Welcome to the Math 1 lesson summary video for the task please be discrete. Discrete.
The purpose of this lesson is to contrast discrete and continuous models for linear and exponential functions while modeling with linear and exponential functions. And again, remember, modeling means we're making tables, graphs, and equations. Whether it's explicit or recursive, doesn't matter, it's all modeling. So the vocabulary we need to be reminded of from the last lesson is that the domain is the set of all input values for a function. Discrete function consists of a set of distinct values. When we talk about set in that case, we're talking about the y values or the x values separately. So they're distinct, whereas in a continuous function, the x values and the y values can take on, they're both sets in which the elements can take on any value within the given interval. So when we look at lesson 3, problem 1, it talks about the Library of Congress receiving books, and they're receiving 8 books per box. So that's because the books they get are fairly heavy, so you don't want to overload the boxes. But we want to make a table, graph, and an equation. So I'm going to make the table in Desmos. So it automatically titles these things, but I can change them to fit the scenario. So if I have n representing the number of boxes, well then if we're receiving 8 boxes per book, then 8n is going to represent the number of books. So for 1 box we'll get 8 books, after 2 boxes 16 books, 3 boxes is 24 books. It asks for 6 boxes and 10 boxes. So I actually answered the equation part first and used that to make my table more efficiently. So 80 books for 10 boxes, 48 books for 6 boxes. And so let's zoom out over here so we can get a clearer picture of what that looks like. So these are just some of the points. So the question we want to ask ourselves now is, would it make sense to connect all the points in between these dots on our graph? So obviously there are points in between 3 and 6 that it would make sense to include, but I'm speaking even more specifically, like in between 1 and 2 here. Would it make sense to have a 1.5 comma 12? So was there a time where they would have received 1.5 boxes of books? No, because boxes come in multiples of 1. So you could have 1 box, 2 box, 3 boxes, only whole numbers. So we can now identify the domain of this function. So this equation here is the equation that we just used to make the table. B of n, where b represents the number of books and n represents the number of boxes, equals 8n. So the domain is going to be the set, and that's what this symbol here indicates, the set of whole numbers. So 0, 1, 2, 3, and that could continue on forever. That's a discrete function because it's a set of distinct values. The distinct values are whole numbers. Nothing in between, nothing outside of that, above or below it, just a set of whole numbers. So this is a discrete function. It's a discrete linear function. As we can see, if I was to connect these points, it would form a straight line. And I could even kind of show you that here. Alright, so let's look at scenario number 2. So in scenario 2, we're now looking at ebooks, and it says 13 ebooks can be downloaded onto the computer each hour. We want to know how many ebooks can be added to the library in 3 hours, 5 hours, or n hours. So I'm going to start with an equation again. Instead of b of n, I'll use e of n for ebooks. And now n is representing the number of hours instead of the number of boxes. And so it's going to be 13n because we can add 13 ebooks per hour. So it's a little more efficient. So I'm actually going to use Desmos to create my graph and my table. So I've graphed it here, y equals 13x. I used y and x because when you're converting between different representations in Desmos, it's helpful to use y and x instead of other variables, because other variables cause Desmos to trip out a little bit. And I'll go back to the home zoom. So I can hit edit, I can duplicate my equation here and convert it to a table. And I want to use just positive values. So we can answer our question here. At 3 hours, that would be 39 ebooks, and at 5 hours, that would be 65 ebooks. and in hours we already said there would be 13 in ebooks that were able to be downloaded. So if I zoom out, we can see how these points from the table correlate to the points on the graph, and we can continue to add points on the graph, whole numbers of hours, and the number of ebooks that would have been downloaded at those times. The question is, in this scenario, do the points on the line make sense in between? So is there a time when after 4.5 hours, 58.5 ebooks would have been downloaded onto the library's computer? And in this case, that does make sense because downloads happen continuously. They are constantly growing closer and closer towards being completely downloaded, whereas the deliveries in the previous problem happen in boxes at set times. So this is a continuous function, and it does make sense to connect those points. So when I want to represent the domain of the function, I can no longer just make a list of a set. So I need to use an inequality. So n can be any number 0 or above, including decimals and rational numbers, everything in between 0 and infinity essentially. So that's why this is continuous, because remember, continuous, it says it can take on any value in an interval. So our interval is 0 to infinity. We can take on any of the values in between 0 and infinity, also known as above 0. So now we can look at problem 5. The policy for the library charges at the Library of Congress is after each day it is past due, they will charge $5 for the first day it's late, and then increase the amount you owe by 10% every day until you end up owing the value of the book. And the value of this book is $25. So we have a scenario where on the first day that it's late, it's going to be $5. So for this scenario, I'm gonna make a table to start with. So first day it's late, day 1, it's costing $5. Day 2, it's going to cost 10% more than that. So 5 times 1.1, it's going to be 5.5. And I have 5.5 times 1.1, that's going to be 6.05. And I'll continue filling in this table. So we can see that by day 5, she is going to be owing $7.33, and it's continuing to increase at 10% every day up until the value of the book, which is $25. So we can use we can write an equation to model the situation to see if it fits our graph. So we're going to say A for the amount that she owes based on, they don't specify what variable we need to use, so let's use D for the number of days. So A of D equals, this is a geometric sequence, which means this is an exponential function. So we're going to have 5 times 1.1, you could put 1.10 if you wanted, to the D power. And notice that that's slightly off from my table of values, which I know are correct. So remember that when we start at the first day, at day 1, we have to multiply, we have to use the D minus 1 exponent to make it fit the points from our data table, because we started with the first day, not with the 0th day. And so now the question is, do these points in between make sense? And that's going to be no, because this is a discrete scenario. They're increasing the charge at a set time each day. So by day 2, the amount that she owes is set, and it won't change until day 3. It doesn't matter whether she comes at 9 a.m. or 11 a.m. on that day to return the book. On day 2, she'll be paying a $5.50 fee when she returns it. So this is an exponential function, and it's discrete. Case 1, problem 1, was a linear function that was discrete, and case 2 was a linear function that was continuous. So we're comparing linear and exponential functions. We're also comparing discrete and continuous. And so notice that the key giveaway that this is an exponential function is the curvature of the graph compared to the straight linear functions. Thanks for watching. If you need help with the Ready, Set, Goes, be sure to check out the Ready, Set, Go videos in the Canvas Student Support site.